day to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on tensor analysis, lecture number 13, which includes the geodesic and its differential equation. Firstly, we define what is geodesic. It is a curve such that for arbitrary displacement, the length of the curve remains unaltered provided the endpoints are kept fixed. That is, integration of ds from A to B, point A to B, is stationary, or derivative of this quantity is 0. We may take 2 points A and B. We may draw different curves from A to B. This curve, this curve. But geodesic is that curve which is unaltered. That means extremum. That means derivative of the length of the curve is 0. It does not change. Now we shall find the differential equation of a geodesic. As we know that the line element is given by ds square equal to gij dxi dxj. If we take differentiation in both sides, we get 2 ds delta ds equal to del gij by del xk delta xk dxi dxj. Now we differentiate this. Other two remain same. Gij delta dxi dxj plus, we take differentiation of this. These two remain same. Gij dxi delta dxj equal to del gij by del xk dxi dxj delta xk plus gij dxj delta dxi plus, now interchanging dummy suffix I and j in this term. So we get ji dxj delta dxi equal to del gij by del xk dxi dxj del xk plus, two terms are same, so we write 2, same in the sense that gij is symmetric, so gij equal to gij. Since gij equal to gij, so This will be 2Gij dxj delta dxi. Now dividing both sides by 2ds, we get delta ds equal to del gij by del xk dxi by ds dxj by ds. Here we have only one ds, here we have used two ds. So ds adjustment del x k plus 2 gi dxj by ds. Here these two operator is commutative, so we may write d delta xi by ds ds. Now taking integration in both sides from point A to B, delta ds equal to integration. Here 2 we have divided also 2 half. Integration half del gij by del xk dxi by ds dxj by ds ds del xk from integration from A to B plus integration A to B gij dxj by ds d delta xi by ds into ds. As we know that for the case of geodesic, this is 0, this is 0. So 0 equal to this A to B half del gij by del xk dxi by ds dxj by ds ds del xk plus A to B gij dxj by ds. Here we may change the dummy suffix I by k. So we may write here k and here also d delta xk by ds into ds. This is number 1 equation. Now we take the second term of equation 1, A to B gkj dxj by ds d by ds del xk ds. Here we integrate this taking this one term and this is the second term. So integration by parts, we get first term g k j dxj by ds, integration of second, this means del xk a to b minus integration of differentiation of first d by ds gkj dxj by ds, integration of second delta xk ds. As by the definition of the geodesic curve, endpoints are fixed, so the change in coordinates at the endpoints delta xk will be 0. Endpoints are a and b. At the point b, delta xk equal to 0. At the point a, delta xk equal to 0. So this term becomes 0. We write here 0. Now differentiate here gkj dxj by ds. Firstly differentiate gkj, del kj by del xi dxi by ds, differentiation of gkj, and dj by ds remains the same. Now gkj remains same and differentiation of dxj by ds, double derivative outside delta xk ds. Now putting this value in equation 1, we get 0 equal to a integration a to b half del gij by del xk dxi by ds dxj by ds delta s delta xk minus value of this integration a to b del g kj by del xi dxi by ds dxj by ds plus gkj into d2xj by ds square outside delta xk ds. Taking left side and taking common delta xk ds, we get integration a to b gkj d2xj by ds square, this term, and then this term, and lastly it becomes negative, this term, and delta xk ds equal to 0. And del xk is arbitrary, so we may write this gkj means term under bracket equal to 0, d2xj by ds square plus del g kj by del xi dxi by ds dxj by ds minus half del gij by del xk dxi by ds dxj by ds equal to 0. G kj d2 xj by ds square plus half del g kj by del xi dxi by ds dxj by ds plus half. This term is taken half and half. Half del G kj by del xi dxi by ds dxj by ds minus half del G ij by del xk dxi by ds dxj by ds equal to 0. Here j is also dummy suffix, I is also dummy suffix. We interchange this dummy suffix I and j. We get gkj d2xj by ds square plus half del gkj by del xi dxi by ds dxj by ds. Here we interchange the dummy suffix I and j. Half del gki by del xj dxj by ds. Here dxi by ds minus half del gij by del xk dxi by ds dxj by ds equal to 0. Implies that gkj d2xj by ds square plus taking half as common del gkj by del xi. Here del gki by del xj. Here minus del gij by xk common dxi by ds dxj by ds equal to 0. Imply that gkj d2xj by ds square. This is the Christoffel symbol of first kind. So we write this ijk dxi by ds dxj by ds is equal to 0. Multiplying both sides by g pk gkj d2xj by ds square plus g pk. This is ijk dxi ds dxj ds equal to 0. Here we get Kronecker delta Pj d2xj by ds square plus here Christoffel symbol of first kind, so Pij dxi by ds dxj by ds equal to 0. Here j is the dummy suffix, j equal to 1, 2, and when j equal to p then 1, otherwise 0. Implies that this is 1 d2 xp by ds square plus visual symbol of second kind ij dxi by ds dxj by ds equal to 0, which is the required equation of differential equation of a geodesic. Now we shall define null geodesic. What is null geodesic? If the distance between 2 points on a geodesic is 0, then geodesic is called null. Since the line element is written as ds square equal to gij dxi dxj. Here ds is 0, right side gij dxi dxj. Therefore the null geodesic is characterized by this equation and differential equation of the geodesic d2xp by ds square plus gamma pij means Christoffel symbol of second kind dxi by ds dxj by ds equal to 0. Now we solve a problem. Problem is that for an Euclidean space referred to rectangular coordinates, geodesics are straight lines. Or so that the geodesic in a three-dimensional Euclidean space are straight lines. So firstly, we have to write the equation of the geodesic. Equation of the geodesic is d2xp by ds square plus Christoffel symbol of second kind dxi by ds dxj by ds equal to 0. Given that it is in Euclidean space, rectangular coordinates. So in that case, metric tensor is constant. Gij equal to constant. Implies that del Gij by del xk equal to 0, derivative 0, constant. For Christoffel symbol of second kind, we write Christoffel symbol of second kind, this equal to GPH, Christoffel symbol of first kind, IJH. Now we write Christoffel symbol of first kind, GPH into half del GIH by del xj plus del GJH by del xi minus del Gij by del xh. This implies that equal to GIH is constant, so derivative of GIH is 0. Similarly, GJH is constant, derivative of this is 0 and this is also 0. So we write GPH into half into 0 equal to 0. This is number 1, this is number 2, this is number 3. So putting the value of 3 in 1, d2 xp by ds square plus 0 into dx I ds dx j by ds equal to 0 implies that d2xp by ds square equal to 0. Here we integrate dxp by ds equal to a constant ap. Again integrating, we get xp equal to aps plus bp, another constant. This is an equation of a straight line. So in the case of Euclidean space, the geodesics are straight lines. Thank you for watching my video. If you are satisfied with my presentation and contents, please click on like button and do subscribe my YouTube channel. Thank you.